Hello, welcome students. Here, in the next coming 30 minutes, we will discuss the partial differentiation of a function. The function which is continuous for its variables. Now, before directly going to definition and what is a partial derivative, let us introduce the necessity of partial differentiation or partial derivatives. In physics, we came across many laws which are expressed mathematically in terms of a differential equation. For example, in case of Newton's second law of motion, which states that rate of change of momentum is equal to the force applied to the body, we can express mathematically in terms of differential equation as d by dt of momentum, that is d by dt of mv, where m is mass of the body and v is its velocity. So d by dt of mv equal to f. Same can be written as m into dv by dt equal to f, where v dv by dt is rate of change of velocity. If y is displacement of the body, then v can be written as dy by dt, so that m into dv by dt changes to m into d by dt of dy by dt, and thus m into d2y by dt square equal to f. So, differentiation of a function, physical quantity and differential equations are important, and we came often while expressing the mathematical form of a law in physics. For example, the laws governing distribution of temperature in the solids, laws governing propagation of electricity in cables, distribution of velocities in moving fluids can be expressed in terms of specific type of differential equations called as partial differential equations. Thus, it is necessary for us to study the partial differentiation and operations involving partial differentiation. So, after knowing necessity of partial differentiation, let us see what is a partial differentiation is. That is, definition of partial differentiation. Before defining definition of a partial differentiation, let us see what is a continuous function. A function, a quantity f, x, y, z, written as f in bracket x, y, z, is a function of three variables x, y, and z. It is a function of x, y, and z. F is function of x, y, and z because the value of f is determined by the values of x, y, and z. Such a function f of x, y, z is said to be continuous at a point a, b, c. Say, for example, if within limit when x tends to a, y tends to b, and z tends to c, f, x, y, z takes the value f, a, b, c. In that case, f, x, y, z is said to be continuous at a point a, b, c. It means when x, y, and z changes, the value of f, x, y, z changes and it takes the new form. Maybe for some value of xyz it is f a b c. In this situation f xyz is continuous at a b c. Now look at the situation that out of three variables x, y and z, only one is varying and remaining two are constant. For example, for a function f x y z, the variables y and z are hold constant, while variable x is allowed to vary. In that situation, f is function of x only, and in this situation derivative of f with respect to x by keeping y and z constant is defined as the ordinary derivative and expressed as dou f by dou x equal to limit h tends to 0 f x plus h comma y comma z minus f x y z divided by h. So this is like a definition of ordinary differentiation, with only the change is that the single variable is changing, allowed to vary, while remaining are constant. So this is dou f by dou x, partial differentiation of f with respect to variable x. So here it is symbolized as dou f by dou x, not df by dx. It is dou f by dou x, partial differentiation of f with respect to x. This dou f by dou x denotes thus a partial derivative or partial differentiation of f with respect to x. The different notations used to denote partial differentiation, one we have seen dou f by dou x, another is capital F subscript small x, and another one is dou f by dou x at the subscript y comma z. So partial differentiation of f with respect to x where y and z are constant. So here we define partial differentiation of f with respect to variable x by keeping y and z constant. Similarly, we can obtain partial derivative or partial differentiation of f with respect to variable y by keeping remaining two, that is x and z, constant. And in this way we can write partial derivative of f with respect to y as dou f by dou y, or f subscript y, or dou f by dou y subscript f x comma z as limit k tends to 0 where f x comma y plus k comma z minus f x y z divided by k. And similarly we can define the derivative of f with respect to z where x and y are constant as dou f by dou z equal to fz dou f by dou z at x and y constant equal to limit q tends to 0 f x y z plus q minus f x y z upon q. So partial derivative of f with respect to x is dou f by dou x, with respect to y is dou f by dou y, with respect to z is dou f by dou z. Now, since partial derivatives, since function f is continuous at x, y, z, the partial derivatives dou f by dou x, dou f by dou y, dou f by dou z are also continuous at f, and they can again be differentiated partially. Now differentiation of dou f by dou x with respect to x is equal to dou to f by dou x square, or simply written as fx comma x. So this is called as second order partial derivative of f with respect to x, or partial derivative of dou f by dou x with respect to x. Similarly, partial derivative of dou f by dou x with respect to y is dou by dou y of dou f by dou x, which is equal to dou to f by dou y dou x equal to f y x. And partial derivative of dou f by dou x with respect to z is dou by dou z of dou f by dou x, which is equal to dou to f by dou z dx, dou z dou x equal to f z x. Now remember the sequence in which subscripts are given to f: f x x, f y x, f y z x. Particularly concentrate upon f y x. It denotes, f y x denotes dou to f by dou y by dou x. That means partial differentiation of dou f by dou x with respect to y, f y x. Similarly, f z x denote dou to f by dou z dou x, f z x. Partial differentiation of dou f by dou x with respect to z. Okay. Now what is order here? Order of differentiation. As we have seen, dou to f by dou x dou y denotes differentiation of dou f by dou y with respect to x, while dou to f by dou y dou x denotes partial differentiation of dou f by dou x with respect to y. Thus, there is an order in a second order partial derivatives, and important to note that this order, which is called as order of differentiation, is immaterial. That means second order partial derivative dou to f by dou y dou x, where order is yx, f y x is equal to dou to f by dou x dou y, that is f x y. So order is immaterial, not important. So order of differentiation for a given function can be changed, since partial derivatives are continuous and function is also continuous. So this is about order of differentiation. Now let us concentrate towards the total differentiation and chain rule in partial differentiation. Suppose a function f which depends upon independent variables x, y. So f equal to fxy is a function of variables x and y. Let us give an increment delta x to x and delta y to y. Then according to Taylor's theorem, f takes an increment delta f. Since f depends upon x and y, it also, and x and y takes increment, so f also takes increment. And increment in f, that is delta f, is written as dou f by dou x delta x plus dou f by dou y delta y plus delta 1 into delta x plus delta 2 into delta y. Equation 1, this we have written directly from Taylor's theorem. Okay. And important to note here that the partial derivatives dou f by dou x and dou f by dou y are continuous. The first two terms from this equation are written as df equal to dou f by dou x delta x plus dou f by dou y delta y, and these are called differential of f. Now If x and y are independent variables, we can write delta x as equal to dx and delta y equal to dy, and thus by replacing delta x with dx and delta y with dy, equation 2 now becomes df equal to dou f by dou x dx plus dou f by dou y dy, and this equation 4 representing df, that df in terms of dou f by dou x and dou f by dou y is known as total differentiation of fxy. So total differentiation of fxy is df equal to dou f by dou x into dx plus dou f by dou y into dy, as it is expressed by equation 4 on this slide. Now, in order to move to chain rule, let us suppose that x and y are functions of three independent variables u, v and w. So f is function of x and y, and x and y are again functions of u, v and w. So we can express x as equal to x u, v, w, y equal to y u, v, w. Now since u, v and w are independent, we can write total differentiation of x and total differentiation of y as dx equal to dou x by dou u du plus dou x by dou v dv plus dou x by dou w dw. This is total differentiation of x, and dy equal to dou y by dou u du plus dou y by dou v dv plus dou y by dou w dw. This is total differentiation of y. Since f is function of x, x is function of u, v, w, therefore we can say that f is function of u, v, w. Therefore total differentiation of f in terms of u, v, w can be written as df equal to dou f by dou u du plus dou f by dou v dv plus dou f by dou w dw. But according to chain rule, this dou f by dou u can be expressed in terms of x and u and y and u as dou f by dou u equal to dou f by dou x into dou x by dou u plus dou f by dou y into dou y by dou u. Similarly, dou f by dou v equal to dou f by dou x into dou x by dou v plus dou f by dou y into dou y by dou v, and dou f by dou w equal to dou f by dou x into dou x by dou w plus dou f by dou y into dou y by dou w. Using the equation 7 in equation 6, we can find that dou f by dou x and dou f by dou y can be taken common, so that in bracket the similar term will be there, and finally we obtain df equal to dou f by dou x in bracket dou x by dou u du plus dou x by dou v dv plus dou x by dou w dw, and second term plus dou f by dou y in bracket dou y by dou u du plus dou y by dou v dv plus dou y by dou w dw, where the brackets are simply dx first bracket and second bracket is dy. So df equal to dou f by dou x dx plus dou f by dou y dy, which is total differentiation of f with respect to x and y in terms of partial derivatives with respect to x and y. So it was about total differentiation and chain rule. Now we came across different types of variables. For example, here we have considered function f as function of variables x and y. The variables x and y, however, can be converted into different types of coordinates known as polar coordinates r and theta, as we have studied in complex variables, where x is equal to r cos theta and y is equal to r sin theta. Thus, x is variable of r and x is function of variables r and theta, y is function of variables r and theta, and can be represented as x equal to r cos theta and y equal to r sin theta, so that we can obtain partial derivative of x in terms of r and theta and y in terms of r and theta, so that dou x by dou r equal to cos theta, dou y by dou r equal to sin theta, and what is dou x by dou theta? It is equal to minus r sin theta, and dou y by dou theta equal to r cos theta. Now, by chain rule, we have dou f by dou r in terms of x, y and r, and dou f by dou theta in terms of x and theta, where dou f by dou r equal to dou f by dou x into dou x by dou r plus dou f by dou y into dou y by dou r. By putting the values of dou x by dou r and dou y by dou r, we can write dou f by dou x into cos